Hello, everyone. I'm Zen. I currently work as a security practitioner at Motional, and I present today an empirical study of OSS-Fuzz bugs. So, gray box fuzzing is a software testing technique that, in a nutshell, feeds smartly random inputs to a program in the hopes of finding bugs. This testing technique is often combined with dynamic analyses to find bugs such as memory violations or undefined behavior, which are also more likely to have security implications. And fuzzing is quite effective in practice, as evidenced by the trophy cases of various fuzzing tools. Given fuzzing's capability to find bugs, Google in 2016 announced the OSS-Fuzz project, where they would continuously fuzz open source software. OSS-Fuzz produces publicly available bug reports. We scraped and analyzed over 23,000 of them, which span over 4 years and 316 open source projects in C, C++, Rust, and Go. By the way, OSS-Fuzz has recently added support for Java and Python. This happened after we stopped collecting data, but for those interested in the OSS-Fuzz dataset, newer data will contain bug reports for these languages. Armed with this treasure trove of OSS-Fuzz bug reports, we can get a glimpse into the state of the practice in continuous fuzzing and examine what do bugs look like, what do these bugs look like, how effective is this testing technique, and look for opportunities to improve. Some of our key findings include, starting off with some good news, we find that OSS-Fuzz quickly finds bugs and developers quickly fix them. This provides real-world evidence that continuous fuzzing is effective as a quality assurance technique. However, we also find that flaky bugs, timeouts, and out-of-memory errors are problematic. This might be bad news for those who are working on fuzzers that find these particular types of bugs more often, since the lower fix rate and the delayed fixes might mean lower impact. And sometimes in fuzzing, there is a bug that appears so often as to block fuzzing of code downstream of that bug. We call these bugs fuzz blockers, and repairing them is important for performance. However, developers tend to fix these fuzz blockers more slowly, which can harm performance. And in our paper, we actually propose techniques to automatically bypass certain common types of fuzz blockers to improve performance without needing a patch from developers. OSSFuzz has also found thousands of security vulnerabilities, but very few of them have received CVEs. This is a problem in open source security because various security tools depend on CVEs as a source of threat information. One remedy is to better inform developers and offer guidance through the CVE process. But also, in addition, Google has recently released the open source vulnerabilities database, and OSSFuzz discovered vulnerabilities go into that database. Security tools can use OSV as an additional source of threat intelligence. And fuzzing campaigns, we find, often find bugs in bursts, where a multitude of bug reports pop up within a short time frame. The danger is that an avalanche of bug reports in a short time frame might surprise developers and possibly even elicit defensive behavior. Thus, there is value in giving some mental preparation to this phenomenon. This is just a brief 4-minute glimpse into our empirical study of OSSFuzz. There's a lot more detail in our paper, and we provide a package on Zenodo, both of which I encourage you to check out.